5.4. The fundamental theorem of calculus. The outline of this video is as follows. We will begin by discussing the mean value theorem for definite integrals, which relates the average value of a function to a specific point in its intervals. Next, we will cover the fundamental theorem of calculus, part 1, establishing the link between differentiation and integration. We will then examine part 2 of the fundamental theorem, also known as the evaluation theorem, which provides a practical method for calculating definite integrals. Following this, we will explore the net change theorem and its applications to displacement and distance. We will also clarify the inverse relationship between integration and differentiation. Finally, we will demonstrate how to calculate the total area between a curve and the x-axis, distinguishing it from the value of a definite integral. We start by introducing the fundamental theorem of calculus, which is the central pillar connecting the two main branches of calculus. This theorem bridges the gap between differential calculus and integral calculus, allowing us to compute integrals using antiderivatives rather than relying on the cumbersome process of taking limits of Riemann sums. This connection was a breakthrough exploited by Newton and Leibniz, fueling centuries of mathematical and scientific progress. Before we fully state the theorem, we will also present the Miesian value theorem for integrals, which guarantees that a continuous function assumes its average value at least once. Essentially, this theorem provides the theoretical underpinning that makes the fundamental theorem work. Let us define the concept of average value for a continuous function over a closed interval from a to b. The average value is calculated by taking the definite integral of the function over the interval and dividing it by the width of that interval, which is b minus a. The mean value theorem for definite integrals asserts that for any continuous function there exists at least one point in the interval where the function effectively equals this calculated average. Geometrically, this means there is a specific height on the curve, f of c, that creates a rectangle with the same area as the region under the entire curve. It is important to visualize this as finding a rectangle that perfectly balances the area beneath the graph. We can now state Theorem 3, the mean value theorem for definite integrals, in more formal mathematical terms. The theorem states that if f is continuous on the closed interval from a to b, then there exists a number c between a and b, such that f of c equals 1 over b minus a times the integral of f of x. We can rearrange this equation to say that the value of the function at c times the width of the interval equals the total integral. This confirms that the area under the curve is equal to the area of a rectangle with height f of c and width b minus a. The key takeaway is that a continuous function always actually hits its average height at some specific moment. This slide presents a geometric interpretation of the mean value theorem. It illustrates a continuous curve y equals f of x and identifies a specific y value, f of c, which represents the average height of the function. This visual helps demonstrate that the area of the shaded rectangle is equal to the area under the curve. It is crucial to understand that the continuity of the function f is a strict requirement for the mean value theorem to hold. If a function is discontinuous, it might never actually equal its calculated average value at any point in the intervals. Consider a step function that jumps from 0 to 1. Its average value might be 1/2, but the function itself is only ever 0 or 1, never 1/2. This discontinuity breaks the guarantee provided by the theorem, as the function skips over the average value entirely. Always check for continuity before applying this theorem to ensure the existence of the value esc. Here is a practical application of the mean value theorem demonstrating how we can deduce function behavior from an integral. Suppose we know that the integral of a continuous function f over an interval from a to b is 0, and that a does not equal b. By calculating the average value, we divide the integral, which is 0, by the width of the interval, resulting in an average value of 0. According to the mean value theorem, the function must assume this average value at some point within the intervals. Therefore, we can conclude with certainty that f of c equals 0 at least once between a and b. We now move to the first part of the fundamental theorem of calculus by defining a new function, capital F of x, as an integral with a variable upper limit. In this expression, capital F of x is the integral of a function f of t from a fixed constant a to a variable x. If the function f is non-negative, you can think of capital F as an area accumulator function that tracks the area under the graph as you sweep from a to x. Note that we use t as a dummy variable inside the integral to distinguish it from the upper limit x. The fundamental theorem states that this accumulated area function is differentiable, and remarkably, its derivative is simply the original function f. This slide presents a visualization of the integral function capital F of x. It shows the area under the curve y equals f of t being accumulated from the starting point a up to the variable point x. This graphic helps establish the geometric intuition that capital F represents the area of the shaded region. We formally state part 1 of the fundamental theorem of calculus, which establishes the inverse nature of differentiation and integrations. Theorem 4 says that if f is continuous on an interval, then the function defined by the integral from a to x is continuous and differentiable. Most importantly, the derivative of this integral function with respect to x is simply the integrand, f of x. This means that if you integrate a function to get an area and then differentiate that area with respect to the upper limit, you get back the original function height. Geometrically, this tells us that the rate at which the accumulated area changes is exactly equal to the height of the curve at that point. This slide provides a geometric insight into part 1 of the fundamental theorems. It illustrates how a small change in the interval width, labeled AH, corresponds to a thin strip of areas. This visual helps explain why the rate of change of the area capital F corresponds to the height of the function f of x. Let us apply the fundamental theorem to find the derivative of an integral defined functions. For part A, we differentiate the integral from a to x of the quantity t cubed plus 1. Simply replacing t with x gives us x cubed plus 1. For part B, notice that the variable x is in the lower limit, so we must first reverse the limits of integration, which introduces a negative sign. Differentiating the negative integral from 5 to x of 3t sine t gives us negative 3x sine x. Remember that the variable must be the upper limit to apply the theorem directly. Now we consider cases where the upper limit is a function of x, requiring the use of the chain rules. In part C, the upper limit is x squared, so we treat this as a composite function where u equals x squared. We differentiate the integral with respect to u to get cosine u, and then multiply by the derivative of u, which is 2x, resulting in 2x times the cosine of x squared. In part D, we first reverse the limits to put the variable expression on top, introducing a negative sign, and then apply the chain rule to the upper limit 1 plus 3x squared. This results in the integrand evaluated at the upper limit multiplied by the derivative of that limit, which is 6x. We now arrive at part 2 of the fundamental theorem of calculus, often called the evaluation theorems. This theorem states that to evaluate the definite integral of a continuous function f from a to b, we simply find any antiderivative, capital F, and subtract its value at a from its value at b. This is a powerful tool because it completely bypasses the need for complex Riemann sum limits. We use the notation of a vertical bar or bracket to indicate the evaluation of the antiderivative at the upper and lower limits. This theorem turns the difficult problem of integration into the typically easier problem of finding an antiderivative. Let us practice using the evaluation theorem on some trigonometric functions. For part A, to evaluate the integral of cosine x from 0 to pi, we find that the antiderivative is sine x. We evaluate sine at pi minus sine at 0, which gives us 0 minus 0, resulting in a total integral of 0. For part B, the integral of secant x times tangent x is secant x. Evaluating secant from negative pi over 4 to 0 yields secant 0 minus secant of negative pi over 4, which simplifies to 1 minus the square root of 2. Here we apply the theorem to algebraic and logarithmic functions. For part C, we find the antiderivative of the terms using the power rule, resulting in x to the 3/2 plus 4 over x. Plugging in the limits 4 and 1, we subtract the value at the lower limit from the value at the upper limit to get a final answer of 4. For part D, recall that the antiderivative of 1 over x plus 1 is the natural logarithm of the absolute value of x plus 1. Evaluating this from 0 to 1 gives us natural log of 2 minus natural log of 1, and since log of 1 is 0, the result is simply the natural log of 2. The net change theorem interprets the integral of a rate of change as the total change in the quantity over an interval. Mathematically, the integral from a to b of f prime of x is equal to the final value f of b minus the initial value f of a. In physics, this has concrete meanings. The integral of marginal cost is the change in total cost, and the integral of velocity is displacement. However, be careful to distinguish displacement from total distance traveled. For total distance, you must integrate the absolute value of velocity. This theorem connects the abstract concept of an integral to tangible real-world accumulation. We will now solve a physics problem involving a rock blown straight up with a specific velocity function. Part A asks for the displacement of the rock over the first 8 seconds. We calculate this by integrating the velocity function, 160 minus 32t, from 0 to 8. Finding the antiderivative and evaluating at the endpoints gives us 1280 minus 1024, resulting in a displacement of 256 feet. This tells us the rock's net change in position is 256 feet above the ground, regardless of the path it took to get there. Part B asks for the total distance traveled, which requires us to account for the direction of motions. The velocity becomes negative after t equals 5, meaning the rock starts falling back down, so we must split the integral at this turning point. We integrate the positive velocity from 0 to 5 to find the distance up, and integrate the velocity from 5 to 8 to find the displacement down, taking the absolute value of the latter. The upward distance is 400 feet, and the downward displacement is negative 144 feet. Adding the magnitudes, 400 plus 144 gives us a total distance traveled of 544 feet. It is useful to summarize the relationship between the operations of integration and differentiation. The fundamental theorem demonstrates that these two processes are effectively inverses of one another. Differentiating an integral of a function returns the original function, while integrating the derivative of a function returns the original function plus a constant. This insight assures us that for every continuous function f, the differential equation dy dx equals f of x always has a solution. Understanding this inverse relationship is key to mastering calculus operations. We must distinguish between the value of a definite integral and the geometric concept of total area. A definite integral can be positive, negative, or 0, as areas below the x-axis are counted as negatives. Total area, however, is always a non-negative quantity and represents the physical surface area between the curve and the axis. To find the total area, we must integrate the absolute value of the function. Practically, this involves splitting the integration interval at any points where the function crosses the x-axis, calculating the integral for each section, and adding their absolute values. This slide presents a visual comparison between two functions to illustrate area versus integrals. The top graph shows x squared minus 4, which dips below the axis, resulting in a negative definite integral of negative 32 over 3. The bottom graph shows its reflection, 4 minus x squared, which has a positive integral of positive 32 over 3. Despite the sign difference in their integrals, The geometric area enclosed between the curve and the x-axis is identical for both cases, 32/3. Let us find the total area between the sine function and the x-axis from 0 to 2 pi. If we simply integrate sine x from 0 to 2 pi, the result is 0 because the positive area cancels out the negative areas. To find the physical area, we split the interval at pi, where the sine function crosses the axis. The integral from 0 to pi is 2, and the integral from pi to 2 pi is -2. Taking the absolute value of both parts and adding them, 2 plus 2, gives us a total area of 4. This slide visually demonstrates the calculation we just performed for the sine functions. It shows the positive region from 0 to pi with an area of 2, and the negative region from pi to 2 pi with a signed area of -2. The total shaded area represents the sum of the absolute values of these two regions. For our final example, we find the area between the x-axis and a cubic polynomial over the interval from -1 to 2. First, we factor the polynomial to find its zeros at x equals 0, -1, and 2, which helps us identify the subintervals. We integrate separately from -1 to 0, obtaining 5/12, and from 0 to 2, obtaining -8/3. We then take the absolute value of the second integral to convert it to a positive area. Adding 5/12 and 32/12 gives us a total area of 37/12. This slide presents figure 5.22, illustrating the cubic function from the previous examples. You can clearly see the small positive area between -1 and 0, and the larger negative region between 0 and 2. This visual confirms why splitting the integral at the zero crossing was necessary to calculate the total shaded area. To summarize, we have covered 4 major concepts in this video. First, the mean value theorem for integrals guarantees a function hits its average values. Second, Part 1 of the fundamental theorem defines antiderivatives as integrals. Third, Part 2 provides a method to evaluate definite integrals using antiderivatives. Finally, the net change theorem and area calculations show us how to apply these integrals to find displacement, distance, and geometric area. We conclude with a few review questions to test your understandings. Consider how the fundamental theorem transforms the problem of finding area into the problem of finding an antiderivative. Also, reflect on the difference between displacement and total distance traveled using the net change theorem. Understanding these distinctions is essential for applying calculus to physical problems.